Okay, welcome back to part 2. Sorry about my audio in the last one. Something was really weird with it. Hopefully I have fixed it for this part here. So let's continue. Okay, so we talked about this Arrhenius equation. We talked about what each of these pieces mean, the frequency factor, the activation energy. Let's put all of this together and consider a reaction. Okay, so let's actually look at something interesting. Okay. So there is a chemical called methyl isonitrile. And it's a really weird looking chemical, which tends to rearrange acetonitrile. Okay, which is kind of another weird looking chemical. Okay, so this is methyl isonitrile. And this is acetonitrile. Okay, now this rearrangement process looks something like this. We have a methyl group attached to an N triple bond C, which rearranges to form methyl group attached to carbon triple bond N. Okay, so that's what this reaction looks like. Okay, let's look at the activation energy. So EA, that's a really bad E. That's a kind of a funny looking E, but it'll work. Okay, so let's look at EA for this reaction. So this is the reaction progress here, and this is energy. Okay, so the energy for the acetonitrile is lower than the methyl isonitrile. Okay, so we start out with methyl isonitrile, CH3, N triple bond C, and the final energy level for acetonitrile is here. Okay, but we have an activation energy barrier to overcome before we can actually get to the product. Okay, this is EA. This is the delta H for the reaction. Okay, so the delta H for the reaction is negative. So this is a, that's a bad H, hold on 1 second. This is a favorable reaction. But again, we have to overcome that activation energy barrier. Okay, and if we look a little bit closer at the frequency factor, so I'm just going to redraw this activation barrier here. Going from methyl isonitrile, as we go up this curve along the progress of the reaction, okay, what's happening here up at the very top is that we have kind of a weird half bond that's formed with a carbon triple bond to a nitrogen here. Okay, so there's some weird semi-bond between this methyl and this CN, and as you can see, this CN can kind of wiggle back and forth in time, and the amount of times that it wiggles, or the amount of times it attempts, so number of wiggles per second is equal to A. Okay, so once it reaches this point here, you can see why the energy is so much higher than in the bound state with N and triple bond C, because this is some sort of weird bond that's happening here. Okay, so it has a much higher energy, and A is equal to the number of times per second that it tries to wiggle into that side formation. Now once it's in this side formation, it can either fall back this way or fall this way. Okay, they're both lower in energy. This is why it doesn't actually happen every time. and why this is a statistical representation of the rate constant. If you remember, the rate constant looks like k is equal to a times the exponential of EA divided by RT. Okay, this term here is called a Boltzmann term. And it's very common in statistics. And as a matter of fact, as you get higher and higher in chemistry, what I mean by that is as you get into higher upper level courses, you'll be using this Boltzmann factor a lot. And it becomes very useful to start to describe chemical processes using statistical factors rather than just looking at it from a non-statistical perspective. And this is simply because there are so many molecules. Okay, so that's what EA and A mean for this reaction. Okay, so A is the number of attempts per unit time. Let's look a little bit closer at this Boltzmann factor. Okay, so this EA over RT. Okay, this is exponential factor, statistical factor. What this actually gives us is a number between 0 and 1. Okay, so it gives us a number between 0 and 1. It's essentially a probability. Okay, and it essentially represents the fraction of molecules that have enough energy to make it over the activation barrier on a given approach. Okay, so it's the number of molecules, or the fraction of molecules, that have enough energy to make it over the activation barrier on a given approach. Okay, so it's kind of like a probability. So it's the fraction of things that are able to get over on a given approach. Okay, the higher the T, the higher the temperature, the higher this factor. Okay, the higher the number of things that can get over the curve. And this makes sense. They have more thermal energy available to them. And if we look at the distribution of the exponential factor, so here we have 1.0 and 0.0 at the very bottom. And if we look at this as a function of temperature, at very low temperatures, the exponential factor is basically 0. But as we approach higher temperatures, it gets closer and closer to 1. Okay, so this is kind of what that exponential factor is doing with respect to temperature. Okay, so the higher the temperature, the higher the exponential factor. The lower the temperature, the lower the exponential factor. Now, let's look at the thermal energy distribution. Okay, so basically the energy of all of the molecules in the system. Wow, that's a really bad graph. I'm just going to start over. Okay, on this axis, x-axis, I'm going to write the fraction of molecules. Okay, and on this axis, I'm going to write the energy. Okay, let's actually extend this a little bit. Okay, so if we have a case where T2 is greater than T1, greater than T1, let's draw the distribution for T1. So T1's distribution looks something like this, maybe. Okay, so that's T1. And T2 is greater than T1, so the fraction of molecules that have a higher energy is going to be greater. So T2 energy distribution is going to look something like this. Okay, so if you can imagine, if we draw the position where the activation energy is, so EA on this graph, the high temperature case has a lot more molecules, a lot higher fraction of molecules that are above this activation energy with just thermal energy. Okay, so you can imagine that the higher the temperature, the more molecules exist in this region above the activation energy, and therefore the faster the rate. Okay, so at high t, this exponential factor is larger. K is larger. K is larger, and therefore the rate is faster. So we can speed up this reaction by increasing the temperature. Okay, make sense? Okay, good. The next question, though, is where do we get these terms, EA and A? How do we measure this? Okay. How to measure EA and A? How are we going to measure them? If we look at the initial reaction, or the initial equation for the rate constant, we have A times e to the negative EA over RT. Okay. And here I want you to pause the video for 30 seconds to a minute and see if you have any ideas. Okay. Try to come up with a way that we could measure EA and A using similar things that we used to measure, for example, the rate or the rate constant, the slope of the rate constant, or the initial concentration. Okay, so see if you can think of a way to do this. Okay, you back? You have an idea? I hope it's something like this. So we can do the same type of thing we did above when we integrated those rate laws, and we can actually write this out in terms of a linear equation. Okay. What I'm going to do to start out is I'm going to take the natural log of both sides. So the natural log of k is equal to the natural log of a plus the natural log of e to the negative EA over RT, which is just negative EA over RT. Okay, I'm going to rearrange this just a little bit, so I'm going to write this as ln of k is equal to negative EA over R times 1 over T plus natural log of A. Okay, do you guys start to see something? You start to see where this is going? We just made this into a linear equation. Y is equal to mx plus b. Okay, so this is the equation for a straight line. M is the slope. Okay, so m is given as negative EA over R, and b is given as the natural log of A. Okay, so this gives us ways to measure this type of stuff. Okay, so if we have a graph, we show the graph here. If we plot the natural log of the rate constant versus the versus 1 over t, okay, we get a straight line, okay, where we start here at the natural log of A, and the slope of this equation is equal to negative EA over R. So now we figured out a way to measure this. This is called an Arrhenius plot. Okay. Basically what you do is you take a bunch of different data points and you fit the data to a straight line, and you can back out the slope, the EA over R, and the intercept of that line, and you can find EA and A. Okay? Now there's a different way, there's another way to do this if you only have 2 points. Okay, so if you have 2 points, you can also solve for EA and A. So this is the 2-point version. Okay. If we have two different points, so let's say natural log of K2 is equal to negative EA over R times 1 over T2 plus the natural log of A. And we have a second point, K1, we'll call it, is equal to negative EA over R times 1 over T1 plus the natural log of A. Okay, so these 2 points are simply measuring the rate constant at 2 different temperatures. Okay, so that's all we did here for this experiment. Is we did two experiments. We measured the rate constant at 2 different temperatures. Okay, now we want to combine them together and see what we can get out of this. So let's do ln K2 minus ln of K1. Okay, and that is equal to negative EA over R times 1 over T2 plus ln of A minus negative EA over R times 1 over T1 plus the natural log of A. Okay? This can be condensed into, after a lot of stuff cancels out, this can be condensed into the natural log of K2 divided by K1. This is using an identity of logarithms here, is equal to EA over R times 1 over T1 minus 1 over T2. Okay? So in this case, we lost all of the info about A. Okay, we lost all the info about A. So when we do the 2-point version, we can't measure A, but it's a good way of measuring EA. Okay, it's a good way of estimating EA. All right. So let's do an exercise where we try to find the activation energy of a particular reaction. Okay, so let's do this. Okay, let's write out the reaction here. The reaction we're interested in is the reaction of nitrogen dioxide reacting with carbon monoxide to form nitrogen monoxide and carbon dioxide. Okay, so essentially the oxygen is flipping from the nitrogen dioxide to the carbon dioxide. And we're going to measure this at a couple different temperatures. So at temperature equal to 700 Kelvin, we measured a rate constant equal to 2.57 per molar per second. Okay. At temperature of 895 K, we measured a rate constant of 567 per molar per second. Okay. Now we want to find EA in kilojoules per mole. Okay. Now take 5 minutes. Take 5 minutes and try to do this on your own. All right. Pause the video. Take 5 minutes and try to do this on your own. Okay, are you back? Did you figure it out? Let's see. All right, so the way that I'm going to set this up is I'm just going to use the 2-point version that we have up here. Okay, I'm going to use this guy right here. Plug this stuff in. I'm going to treat this as, let's see, this is K2, and this is K1. This is T2, and this is T1, and just plug it into the equation above. So I have ln of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. Okay, so I just need to plug stuff into that. Let's start out. Natural log of K2. K2 was 567 per molar per second, divided by 2.57 per molar per second, is equal to EA over R times 1 over T1 was 700K minus 1 over T2 was 895K. Okay, these units cancel out here, and we end up with just a number on this side, which ends up being 540. Okay, and that is equal to EA over R times, if you compute out this value here, you get 3.09 times 10 to the minus 4 Kelvin inverse. Okay, now we solve for EA, and EA is equal to 5.40 times 1 over 3.09 times 10 to the minus 4 Kelvin times 8.314 joules per mole Kelvin. Okay, and then we're going to multiply this to get it into kilojoules per mole, which is just multiplied by 1 kilojoule is equal to 1,000 joules. Okay, so we cancel out joules there. We canceled out Kelvin, so now we end up with kilojoules per mole, and we get EA is equal to 1.5 times 10 to the 2 kilojoules per mole. Okay, there we go. That's EA for you. And I hope that's what you got in your example as well. Oops, forgot to change black. Okay, so that's an example. That's kind of how you would be given it in an exercise or on an exam. Okay, so the next part gets into something else. So I think that I will end this here, and we will get back to this on Friday. So I'll see you then, and I hope you have a good couple of days. Again, email me if you have any questions, and we'll talk Friday. Take care.